and parsing will be based on context-free grammars. So in today's lecture, we will be basically reviewing context-free grammars. So the lecture will be about reviewing, not introducing context-free grammars. So I assume that you already know context-free grammars, and you have seen them in 135, and you have written many grammars. But we are reviewing them now. And then we will learn how to use these grammars to build a parser. So in the first stage of the compiler will do scanning. And the scanner will divide, it will divide the input string, which is a program. By the way, your program will be viewed by the scanner as a string of characters, no matter how big your program is, how many lines, how many lines of code it has, it will be viewed as a string. So if you have something like x 2 3 4 equals 5 7 9, and the scanner divides this into words or tokens. So this is this will be an identifier. This will be a number. By the way, in this, when we talk about parsing, there will be little advantage in doing both integer and floating point numbers. So we'll just focus on integers. So there will not be any actual benefit in doing both integers and floating point or real numbers. It will be the same concept from parsing point of view. From scanning point of view, they are treated differently, and we know how to write rules for integers and how to write rules for floating point. But from parsing point of view, a number is a number. So in this, in our treatment of parsing, we'll just say a number, and we will limit ourselves to integers, but it's not very limiting because floating points will be treated the same way by the parser. And this is our assignment, and this is our semicolon or end of statement. Now, what's interesting in the compiler is that these parts of speech that the scanner identifies, these will become the symbols of the alphabet that the parser deals with. So our alphabet, at the parsing level, the alphabet is going to consist of an identifier. So this whole identifier is just one symbol of the alphabet, and this comes from the scanner. A number is another symbol of the alphabet. The equal is another symbol of the alphabet. Plus, minus, multiply, if, else. So from parsing point of view, each one of these will be viewed as a single symbol of the alphabet. So this is one symbol. This is one symbol in the alphabet. So there are two levels. There is the scanning level, where we do the micro syntax and we identify the words of the language. And there is the parsing level. And at the parsing level, these words become individual symbols in that language that we will be trying to recognize using context-free grammars. Of course, some of them will be just individual characters. So this symbol is just an individual character. But this, from parsing point of view, this will be treated as a single symbol, and this symbol is the keyword else. Okay? Yeah. So the scanner will return to the parser. Basically, the way this works is the parser will call the scanner. The parser calls the scanner, and the scanner will return a part of speech. So it will return, identifier, number, whatever, and it will return also the actual lexeme. Or a clearer way of doing this is get next word. So when the parser does get next word, it's calling the scanner to get the next word in the input stream. So with this example, the first time this get next word will return an identifier. It will say, okay, the first word is an identifier, and this is an actual lexeme. Then when the parser calls get next word the second time, it will return this. It will tell it the next word is the assignment operator, and the third word is a number. Okay? Yes?
Well, I had two questions. So the scanner doesn't operate on the entire input and then just pass it as a list to the parser. It actually gets called for each word.
Yes.
Okay.
Yeah. So, well, in principle, you can do it both ways, but in practice, yes, it will return one word at a time.
Okay.
The scanner returns one word at a time.
Okay. The second question is, when the scanner encounters something like a number, does it do the conversion into an actual number format, or is that the job of the parser?
Okay, so all what the scanner does is that it identifies this as a syntactic category. It says it's the syntactic category number, and then it will give the parser the actual scheme, the lexeme, sorry, which is 579. Okay, so this is the lexeme, and then the parser deals with this. In fact, doing the actual conversion is neither scanning nor parsing. It's scanning is about identifying words, and parsing is about identifying sentences or statements. But yeah, once this has been identified as a number, we can do the conversion. It can be done, as a it can be done in scanning or in parsing, but in principle, it does not belong to either scanning or parsing. As conceptually. Okay, so now this is going to be our alphabet, but in today's lecture, we will focus on a simple alphabet, the basic alphabet that you have probably seen in 135, which is the alphabet AB, the alphabet that consists of 2 characters AB, only to review the concept of context-free grammars. So in today's lecture, we'll focus on this alphabet, but in subsequent lectures, this is what we will be focusing. This is what our alphabet will be. Okay. So, a context-free grammar, how would you describe a grammar? So since this is a review, since we're reviewing grammars, how would you describe it or define it? Yeah.
The explicit rules of a language?
Yeah, it's a set of rules. Basically, a grammar is a set of rules for defining a language that recognize or that generate a certain language. And a language, a formal language, when we say language here in this context, it's just a set of strings. A formal language is a set of strings. So it's a set of rules that generate all the strings that belong to a given language. A set of rules that generate all the strings that belong to a given language. Now, if that language, and again I'm talking about formal languages, if that language is regular, then we don't need grammars. We can recognize that language using a finite automaton or a regular expression. In fact, we can use grammars because grammars are more general. And the special kind of grammars that generate regular languages, we call them, what do we call the grammars that generate regular languages?
Regular
grammars. Exactly. So there is a subset of the grammars, or a subset of context-free grammars. In fact, context-free grammars are also a subset of the big set of grammar context-sensitive grammars. But a subset of context-free grammars is the set of regular grammars that recognize regular languages. Now, here we focus on those languages that are non-regular, that cannot be recognized by finite automata and regular expressions. And maybe the classical example of a non-regular language is this language. the set of strings W such that, or no, in fact, I'll write it this way, the language AN, BN. Of course, like I said in today's lecture, we'll focus on this alphabet AB, such that N is greater than 0. So this is an example of a non-regular language. It's a language that cannot be recognized by automata and regular expressions, but can be generated using a context-free grammar. And the context-free grammar for this language is S. So does anyone remember this? This is probably the first example that you have seen in context-free grammars. ASB or
empty.
or epsilon. Okay. So we do need a review. Okay. So this is a context-free grammar. Now, how many rules or productions does this grammar have?
One.
2. It has 2. So this is one production. In fact, these are 2 productions that are merged together. We could have written this as, S is ASB or S is epsilon. So we could have written this as 2 separate rules or productions. So each one of these is called a rule or a production. But usually it's more convenient to write it this way. If there are multiple rules that define the same symbol, we can do them this way, where this bar stands for what?
Or.
Or. So this stands for or. So it's like S is either ASB or epsilon. Okay? We can write it this way, or we can write it this way. Okay. Now, in this case, a grammar, what do we call the S?
Non-terminal?
Okay, it's a non-terminal, but it's a special non-terminal.
The start.
The start variable, yeah. So the grammar has, I think we can get rid of this now. So a grammar consists of V, T, P, and S. So it's a quadruple that consists of 4 sets. The V is the set of variables. Or there's another name for variables in this context. Variables are non-terminals. So variables are non-terminals. Non-terminals. And T is a set of terminals. P
The production.
set of productions.
Yeah.
And S, there is always one distinct variable, the start variable. So in this case, in this example, we only have one variable, which is S. We have 2 terminals, A and B. And S, the only variable that we have, happen to be the start variable. And we have 2 productions that are written in this way. Okay? So this is an example of a grammar. We will see more grammar examples in this lecture. Now, the terminals, the set of terminals, you can also view it as the alphabet for the grammar. It's also the set of symbols that can appear in a string that belongs to this language, or a string that is derived from this grammar or generated by this grammar. Now, in the context of programming languages, our sigma, like I said, it will not be AB. It will be, sigma will be identifier, number, the different keywords, the different operators. Okay, so now let's look at this. Let's do what we call derivation. So let's derive derivation for A, B, B, B. So how do we derive it? We start with the start symbol, or start variable. Then, in each step, we make a substitution. So in order to derive this string from this grammar, the first substitution is going to be A, S, B. And of course, terminals, you cannot substitute for terminals. By the way, here I'm using the convention of, I'm following the convention of writing terminals in lowercase and variables in uppercase. So this is the convention that I'm using. Terminals are in lowercase, variables are in uppercase. So in our convention, these are lowercase, and these are, the variables are uppercase. There are other conventions, some people use, some people underline terminals. So there is another convention for writing grammars where people underline terminals. So in this case, we substitute ASB for S. So at any step, you can substitute for S either this or this. You have two possible substitutions because you have two possible rules or productions. And for this S, we also substitute ASB, and we do it again, ASB. Then, in the final step, we substitute epsilon. So the string that we have just derived is this string, A, B, B, B. So the string that gets derived consists of the leaves of the tree. So this is what we call derivation tree. This is the derivation tree. And the string that gets derived will appear on the leaves of this derivation tree, and we read it in order, left to right. So this is basically going to be, this is the first symbol in the string. This is the second, third, fourth, fifth, sixth. Okay? So this is the string that we have just derived. So this is a derivation tree. And remember, in compilers, our goal is to read a program written in a source, some high-level language, and construct what we call the abstract syntax tree. And the abstract syntax tree is going to come from this derivation tree or parse tree. And the difference between the abstract syntax tree and the parse tree is that in the abstract syntax tree, we only keep the nodes that correspond to actual operations. And we get rid of the nodes that correspond to grammatical symbols. We don't care about symbols in the grammar. We care about nodes that correspond to actual operations, such as add or multiply, operations that will get translated into actual code. Because we are building the abstract syntax tree in order to generate code. We will get to that. So we don't have to fully understand the difference between the derivation tree and the abstract syntax tree, in fact, until we are done with parsing. And parsing, like I said, will take 3 weeks. So this week we'll basically learn how to write grammars for actual programming language constructs. The second week we will look into one approach to parsing, which is top-down parsing. And the third week we will look at bottom-up parsing. So there are two approaches to parsing, top-down and bottom-up. So each one of them will take roughly a week. Okay, so this is an example. By the way, you can also do the derivation in a textual format, so you can do the derivation like this, S, then you substitute for S, ASB, then you substitute for this as another ASB, so this also derives ASBB. So what you did here is that you substituted for this S, this. So this got substituted for this based on this rule, because I have a rule here that says I can substitute ASB for S. Then there is a third step where we do S. Sorry, yeah, this should be a B. 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 And again, I have substituted now for this S, I have substituted this. And last step is substituting an epsilon for the S. So I will end up with B. Usually we don't write the epsilon. You can write the epsilon, but usually we don't write it. And this leads to the string that we are trying to derive. Okay, so let's look at another example now. So, about let's n greater than or equal to 0, and m is greater than n. So now we need another grammar for this language. Okay. So a grammar for this language, the language of A's and B's, where the number of B's, of course A's followed by B's, where the number of B's is greater than the number of A's. In fact, there are two ways of thinking of this. So you can think of it this way. B, 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 B. So you can think of it as this is a string that belongs to the language of equal A's and B's, and then we are adding some additional B's. So this is one way of thinking of it. Another way of thinking of this is the following. You can think of it as A, B, 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 B. And you can think of it as this being the core or the center or the middle part of the string. So this is a string that has more B's than A's, a string in which the A's appear before the B's, and there are more B's than A's. There are two different ways of thinking of this string, and each of these two different views will lead to a different grammar. So in this case, I can construct a grammar for this by saying, okay, this grammar will consist of S1 followed by S2, where S1 is a grammar that belongs to the language of equal A's and B's. So S1 is going to be AS1 B or epsilon. So S1 is a string that belongs to the language of equal A's and B's. And S2 is going to be what?
B's.
All B's. All B's.
So it's going to be S2B, then S2.
Yeah, so it's going to be B, S2. So this is the recursion. We can repeat or
B.
Yeah.
Epsilon.
No.
No, if you add epsilon, it will be wrong. Why?
You need at least one.
Yeah, because then you can substitute epsilon for S2, which means that you can have equal number of A's and B's. So if you substitute epsilon for this, you will have a string with an equal number of A's and B's, and that string does not belong to this language because in order for the string to belong to this language, it has to have more B's than A's. Okay. So epsilon is wrong,
Okay.
but if this had been greater than or equal to, then epsilon would have been correct. Okay, so equality is not allowed. So this is one view of this string. So S1 is a string with equal A's and B's, and S2 is a string with a bunch of B's. Now here, we can look at this as a string that has S is ASB or, so this or gives you the central part of the string, or B, where B is what?
At least one
S2.
B.
Yeah, so it can be like S2. You can call it S2, by the way, or you can call it any name, B or C. So so let's do a derivation for each one of them to understand what's going on. So let's do a derivation for this. So let's derive this string. To derive this string, we will have S, and S consists of S1, S2. Okay, and I think this will not fit, so we'll. Okay, yeah, let's do it here. So S is going to be S1, S2, right? So this is our S1 and this is our S2. And S1 is going to derive two A's and two B's. So it's AS1B, AS1B, and then epsilon. So now we derive the equal number of A's and B's. Then we derive for S2, we can have B S2, it's BS2. BS2, then what should we do? Another BS2. Another BS2, then, oh, sorry, so we only need one B, so we have to substitute one B. So now this gives us equal number of A's and B's, and this gives us two extra B's. And again, the derived string is, you can read the derived string by looking at the leaves from left to right. So this is going to be symbol number 1, number 2, number 3, number 4, number 5, number 6. Look at the leaves of the tree. So the terminals that appear on the leaves of the tree, and you read them from left to right in order. Okay, so let's do the derivation here. So the derivation for this is going to be what? So it's going to be, this is our B. Okay. And in the middle we have ASB. So we will do ASB. Then we will do ASB. Then the central part is going to be a B. And this B is going to consist of B, B, and this is a B. Okay, so here This is number one. This is number two. This is 1, 2, 3, 4, 5, 6. Okay? So everyone now remembers context-free grammars? Oh, by the way, what do we mean by a context-free grammar? Why are these grammars, or both of these grammars, are context-free? What is a context-free grammar?
It's because the variable can appear anywhere within the symbol string. It's either left or right.
Okay. No, you are defining a non-linear or a non-regular.
Yeah.
Yeah. So this is what makes a grammar context-free as opposed to context-sensitive.
There's only one derivation for each string. There can't be more than one.
One derivation for each string?
For a given grammar.
Or for a given grammar, there is only a single derivation for a string?
Yeah.
So that's the definition of what? So you're defining something else. If there exists a single derivation for a string, then the grammar is called
Non-redundant?
non-ambiguous.
Non-ambiguous.
Yeah. If there are multiple derivations, it's ambiguous. If there is only a unique derivation, it's non-ambiguous. So you are defining ambiguous versus non-ambiguous. But what's the definition of context-free versus context-sensitive? So in a context-free grammar, all the variables that appear on the left-hand side, or whatever appears on the left-hand side, is an individual variable. It cannot be multiple variables. So you cannot have something like, ASB is, ASBB, something like this. So on the left-hand side, what you have on the left-hand side is a single variable. That makes it context-free. If on the left-hand side you have variables and terminals, then in that case it will be context-sensitive. And context-sensitive, we're not interested in context-sensitive grammars in this course because programming languages can be defined using context-free grammars. So that's why we are limiting ourselves to context-free grammars because that's what we need to define the syntax of a programming language. Just we need to know what context-sensitive is. All what we need to know is what does it mean for a grammar to be context-free as opposed to context-sensitive. Okay? Okay. So everything that we will cover here is going to be context-free, a context-free grammar, or CFG. Although I hate to write this in a compiler course, because CFG in a compiler course is an acronym for something else, which is control flow graph. So it's I hate to use this acronym because it's overloaded. It means context-free grammars and it means control flow graph. Okay. So let's take another example. So how about this grammar? S is ASB or BSA or SS or absent. So this is a grammar. How many productions do we have here? 4 productions. So each one of these that are connected with the OR, each one of them is a different production. We could have written each production separately. So this is production 1, production 2, production 3, production 4. And we still have one symbol or one variable, which is S, and we have 2 terminals, A and B. Now the question is, what's the language that is defined by, or that is generated by this grammar?
Even length strings?
It's
Even
Palindrome?
length, it's, well, it's more restrictive. So this is an even length string
Yeah. Wouldn't it be?
that does not belong to the language. So this is an even length
Yeah.
string that does not belong to the
It would
language.
be
So
a-
it's not only even
It-
string.
it'd be
Strings
a
with the same
palindrome
number.
Almost.
yeah.
Strings with the same number of A's
It
and
can't be
B's.
almost. So it's either a palindrome or not. There is no almost.
Same number of A's and B's.
Yeah, exactly. So it's the same number of A's and B's. And it's, by the way, the grammar for a palindrome is this. So palindrome is ASA or BSB.
Yeah.
Yeah.
Or, so
Yeah.
if you want it to be an even length palindrome, you put an epsilon. If you want it to be an odd length, if you want to
Put an
accept
extra
odd length
AB.
palindromes, also you can accept A and B. So this is the palindrome grammar. Okay, so for this language, is the set of strings W such that there is a notation for the number of A's that we would like to use, which is NA of W equals MB of W. And we will define NA here. NA of W is the number of A's in W. And of course, MB of W is the number of B's in W. Okay, so it's the language that has, in which the set of strings in which the number of A's is equal to the number of B's. Okay. So now, this language, let's derive for example, let's get it. So this is the palindrome language. So let's do a derivation for A, B, B, A. So in order to derive this, we can think of this as, this is one S and this is another S. Okay, so we derive this. This is one derivation. S is SS, two S's. The left-hand S is going to be AB repeated twice. So it's going to be ASB, ASB. And then what should I substitute for this?
Epsilon.
Then the right hand S, I will derive B S A. Okay, and then I will substitute epsilon. Okay, so this is one derivation. In fact, I could have derived this. This is also another valid derivation. I can put, S, then this S I can substitute an epsilon, then this S is going to be the same as this. So this, I can put this here. So this means that I have at least two derivations. When I have at least two derivations for the same string, then the grammar is ambiguous. This is an ambiguous grammar because this is at least another derivation for the same string. I can do this, and then this S is going to have the same tree that I have here. Okay, so when you have multiple derivations for the same string, we call this grammar an ambiguous grammar. Now, so let's make the distinction between a leftmost derivation and a rightmost derivation.
Yeah.
So,
That's what I was thinking.
okay. So in a leftmost derivation, we make the substitution for the leftmost variable. In the rightmost, we make the substitution for the rightmost. What does this mean? So in order to, let's do the derivation for this again. So for this, we do S, we substitute for S, SS. So when we do the derivation this way, so let's do leftmost. When we do the derivation this way, we make one substitution at a time. So now the question is, should we first substitute for this S or this S? If it's a leftmost derivation, then we substitute for this S. If it's a rightmost derivation, we substitute for this first. So this is a leftmost derivation. Then we substitute for the left. In this case, substituting for the left is A, S, B, and the right S remains the same. Then again, we substitute for the leftmost variable, which is this. So we're going to do again A, S, B, B, S. Then we do, what's the next substitution in this case? Epsilon for this. So it's going to be A, epsilon, B, B, S. Then the last step is going to be, no, there will be more steps. So it's, we will start substituting for this S. Then we'll have A, epsilon, B, B, and B, S, A. Then the next, or the last step is A, epsilon, B, epsilon, A. So this is the leftmost derivation in which we substituted for the leftmost variable. Whenever we have, this is the sentential form, by the way. This is sentential. It's any intermediate step in the derivation that has a mix of terminals and non-terminals. It's a sentential form or an intermediate form. Okay. So the first step, we have the start symbol. At the very end, we only have terminals. And in the middle, we have a mix of terminals and non-terminals. Okay, so let's do a rightmost. Rightmost derivation. Okay. SS. Then we substitute for the right. So substituting for the right is going to be S, B, S, A. Then this is going to go to S, B, epsilon, A. So we did this part first. We did the right first. Now we are left with the, we're done with the rightmost part. So now we substitute for the S. So we will do A, S, B, B, epsilon, A. Then this derives A, S, B, 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 epsilon, A. Then this, at the end, this we substitute for the S, A, epsilon, B, 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 epsilon, A. And then you can get rid of the epsilon because it's the empty string. Okay, so now the point is, if a string has, usually a string will have a leftmost derivation and a rightmost derivation. Unless the grammar is very simple, there will always be a leftmost and a rightmost. So having both a leftmost and a rightmost doesn't mean that the language is ambiguous. A language is ambiguous if you have two leftmost or more than one leftmost derivation or more than one rightmost derivation. Or in other words, you have more than one derivation tree. In the derivation tree does not specify the ordering for the derivation. So this derivation tree is not leftmost or rightmost. You can't call it leftmost or rightmost because we don't have the notion of ordering, the ordering of the substitution. So this tree corresponds to both the leftmost and the rightmost. So both of these derivations correspond to this tree. Okay. So a grammar is ambiguous if there are multiple trees, there are multiple derivation trees. Okay. Now, why do we care about derivation? Because in fact, what parsing is all about, it's about finding a derivation for a string. So your program is a string that belongs to that programming language, and the parser is trying to find a derivation for that. Given the rules, the productions or the rules that we will write to define the programming language, a parser is that stage in the compilation that looks at the rules and the program, which is just a string of characters, and it tries to find a derivation for that string. So your program, even if it's a million-line program, is a string that should belong to the, must belong to the language defined by the context-free grammar for that programming language. And then it will construct a derivation tree for that string, and then that derivation tree will become the abstract syntax tree. Okay, so parsing is automated derivation. So it's a program that does the derivation. So we will be studying some algorithms for doing the derivation. Now we are doing the derivation by inspection. We don't have a specific algorithm for doing the derivation. We have small grammars and small strings, and we are doing our derivation by inspection. But this will not work for a compiler that needs to parse a potentially, a program with an arbitrary length. It needs to parse a program that has millions of lines of code. So we need an algorithm to automate the derivation, to figure out a valid derivation for a string, or to determine that no derivation is possible. And if no derivation is possible, what does that mean?
Compile error.
Syntax error.
It's a syntax error, yeah. If the compiler cannot find a derivation, then that's a syntax error. Okay, so this is what we will be doing in the next lecture. Next lecture we will start writing grammars for actual programming language constructs. So today's lecture was about reviewing the concepts of context-free grammars and derivation, leftmost derivation, rightmost derivation, ambiguous grammars, all of these concepts. Next lecture we will start writing grammars for actual language constructs, and we will start with expressions. One of the fundamental constructs is an expression. Any questions on today's lecture? Yeah.
When the compiler is doing the derivations, what's the time complexity on that? Is it like fast or?
Oh, yeah, it's fast. So it's going to be, yeah, we will see. It's very fast compared to other stages in the compiler.